Hello everyone, welcome to Tactica Imperialis and to today's video. Today is going to be another of my Tactica Tutorialis science lesson videos. We're back in the classroom, it's been a while, but we are back. Today's lesson is going to be a GCSE combined science lesson drawing from one of the physics topics. So even if you're not a triple science or a triple physicist, then you still can get something out of this lesson. And even if you're in Key Stage 3, some school curriculums do teach this stuff at Key Stage 3, though maybe not in the same detail. So this might be a useful little building block or a recap or spoiler for you if that interests you. So today's lesson is going to be all about forces, but we're going to introduce them through two things. We're going to look at Newton's laws of motion, and we're going to look at resultant forces. We're not going to look at what forces actually are. We're not going to get into that, but we're going to look at predominantly the effects of forces and then the calculations that we can do with them on things like acceleration, which are some of the most fundamental calculations that you need for a lot of motion-based physics, which happens at GCSE, it happens at A-level, it happens at university. You do this sort of thing a lot, and it all sort of starts here. So the way this lesson is going to work is very similar to our previous ones, where it's going to be exercises and sort of lecture segments, but I'm going to change the formula ever so slightly. So in order to prevent this video going too long, I'm going to remove the solutions videos segments from this video. If you want the solutions and the answers to the exercises that we do, then they are going to be linked in the description. They are unlisted, so you won't find them in the subfeed. They are in the description, and they're going to be clearly signposted for you to check your answers to the various exercises. That way, those who do the exercises can get their answers checked, and those who don't want to do them can move on through the video without sitting through 15 to 20 minutes of me going through answers that they don't care about. I just thought I'd decide to do that because it saves the video from being too ridiculously long, and I know that I have made lessons that are nearly an hour long before, so hopefully we'll speed this one up a little bit. So we've got plenty to cover. Plenty of interesting stuff and a lot of discussion points to have along the way, and plenty of exercises for you to do. So without further ado, get your books, get your pens, or whatever you want to write on, and let's begin. So to start us off today, rather than having a particular activity, something with solutions, since this is going to be for some people a real introduction to Newton's laws and forces, I thought what we'd do is have a bit of what we call in physics and science a thought experiment. In fact, I'll put it in air quotes, a thought experiment. So this doesn't happen, or for example, this isn't happening, but it is something that you can visualize and think about in your mind using your understanding of the real world and maybe making some educated guesses about forces. So right here, we have a person sat on an armchair. I know I'm an absolute genius at art. I'm not. But there's a person sat in an armchair right now, and they're just sat there, chilling. Maybe they've dozed off and fallen asleep. I don't know. And I have a few questions. So the first of my questions is, well, why aren't they moving? That's my first question. Why is it that this person is not moving? Because as I just told you that they're not moving right now. They might even be asleep, so they're not consciously controlling their muscles to keep them in place. They're just not moving. Why? Second question, what would make them move? So what would make this person move? And no, I will not accept as a theoretical answer being jump scared awake. We're in physics here, so try and think a little bit more physics than that. What would you have to do to make that person move, or make the chair move? Because we're going to treat this whole as one system. The third question that you might want to ask, which is something that's a little bit more Well, it is one of Newton's laws, so I think it's completely fair to say. This chair is not floating in space, let's be realistic here. This chair is probably sat on the floor. There's probably a floor underneath them. But they just sit there on this floor or carpet and nothing happens. So I guess the question is, why don't they fall through the carpet? So you might want to consider, when you answer question 1, when you get to question 3, it may make you rethink question 1. And we will return to this a little bit later. In fact, this very individual is going to be the source of our final test question right at the end of the lesson. I'll probably draw it again, but worse. And we're going to apply everything we pick up today to this person sat in their chair and try and answer these questions. So keep them in mind, maybe write them down or screen cap if you're on a mobile device, and have a think. Why is this person who's probably asleep in their chair not moving? What would we have to do, or what would cause them to move? And as I said, no, jump scares don't count. And if they're sat on some carpet, like on the floor, why don't they fall through it? Because it's not like they can't fall through things, they fall through the air. So why don't they fall through the carpet? Some questions to think on, and we'll try and answer them as the lesson goes on. But for now, let's get on to Newton's laws. All right, let's get into Newton's laws. Now, Newton made 3 laws. And if I'm being completely honest, as a scientist with you, I shouldn't really call it a law, because realistically I need to put that in air quotes, because all of scientific theory actually is exactly that, it's theory. This is Newton's suggestion based on what he observed, and as far as we can tell, it is correct and it works, but it is not empirical anything. Science is not a pile of facts. It's actually kind of just a pile of best guesses. And people sometimes need to get out of the idea that the science said it, therefore it must be true. Science is constantly evolving. So I'm going to put law in air quotes. So Newton's first law is to do with objects that are not moving, or objects that are not what we call changing their state of motion. So I'm going to give you the most of the quote, and then we're going to explain what that means. An object will remain. Now I appreciate this is quite long-winded. It's actually very simple when you put it in terms of resultant forces and whatnot, which we'll do later, but these are the laws. An object will remain in its current state of motion unless, and we'll finish that quote in a moment. So first off, we need to explain what a state of motion is. So a state of motion could be something very, very simple. It could be that. The state of motion of my tape measure is it's not moving. It is stationary. And that is its state of motion. It might be that my tape measure is just being pushed along this whiteboard at a constant speed. That's roughly a constant speed. And that is also a state of motion. Now, when things start going around corners and accelerating and doing all of this stuff, it gets a bit more complex. Basically, a state of motion, as far as we need to understand it, is stationary or a constant speed. And we'll write some definitions down here. So, an object will stay like that unless something in particular happens. And this is where forces come in. Because, to use my tape measure again, if my tape measure just sits there, it's going to stay sitting there. And nothing is going to make it spontaneously not just sit there. I have to come along and push it or pick it up for its state of motion to change. So what we say is unless an external force, actually no, not an external force, that's being a bit too picky. So we'll be a bit more general and say unless a force acts on it. And that's the quote. An object will remain in its current state of motion unless a force acts on it. So that's it in science speak, but what does that actually mean? Well, as you've seen with the tape measure, as I keep coming back to as the example, it will not change what it's doing unless you make it change it. And this is going to be some terminology I'm going to introduce now, and we'll come back to it later. So if we have what we call balanced forces, or there are no forces, the object will stay still, or, and this is a big or, keep moving at a I've written the word at twice. I'm doing so well. We'll keep moving at a constant speed. Now we'll come back to that idea of balanced forces a little bit later when we get to resultant forces. But what I'm essentially saying is, unless there is a force to make an object stop doing what it's doing, it's going to keep doing what it's doing. Normally, what it's doing is one of two things. Sitting still and being stationary, that's the sort of proper term, is stationary with an A, not an E, that's what you buy for like a pencil. Or it moves at a constant speed, because though in that situation, the forces are actually balanced, and we'll see why when we get to Newton's second law, well, right about now. So, Newton's second law. This is the most famous one in terms of equations. In fact, finding it in word form is very difficult. Most of the time, you will see Newton's second law written pretty much entirely mathematically, and the definition relates to its equation. So, don't take this as this is what Newton wrote, because it isn't, but I think it's a good way of explaining it. So what I'm going to say is, if there are unbalanced forces, and I'm going to put in brackets another new term, which is a resultant force. Again, we will define this later. I'm just giving you the term now because it will help make everything make sense. A resultant force, the acceleration of the object is directly proportional, which is another sort of scientific term, to that force. Now that's a lot of words, and again, it's some terminology that probably has confused a couple of people, and I completely understand why. So let's go through that sentence and put it in simpler terms. And I'll give it you in equation form. This is Newton's second law, and this is all you'd ever be asked to write down pretty much in an exam, and it's certainly what you'd be expected to use. F equals ma. One of, if not the most famous equation in physics, with the possible exception of E equals mc squared. F equals ma. Force equals mass times acceleration. So if there is a force applied to an object, then that object will accelerate. And the acceleration times by a constant, that being the object's mass, is equal to the force applied. So to come back to my trusty tape measure, my tape measure at the moment is sat still. I'm now going to push it. So I'm going to apply a force to it, which is going to unbalance the forces on it. It's going to cause the force to act and leave what's called a resultant force behind. So if I push it, if I give it a bit of a shove, the tape measure now starts to move. It wasn't moving before, but now it is. It is accelerating. It is starting at a speed of 0 or a velocity of 0, and it accelerates because of the force applied. And it actually accelerates in the direction of that force. So if you're doing this at GCSE, then you'll have been introduced to the idea of vectors. Force and acceleration are both vectors, meaning they have a size and a direction. And that means that whatever direction the force is applied in, whether that's to the right, to the left, up, down, whatever, the acceleration and therefore the change in speed and thus pretty much the movement is in the same direction. It gets a bit more complicated when you get to A level, but vectorially that's what that means. And it is directly proportional because F equals a constant multiplied by A. M for the object is going to be a constant. We're not going to change the object's mass. So that's Newton's second law in long form. Realistically, that is Newton's second law. That's really all you need to know. F equals ma, and we'll do some calculations using this later on to make sure you've got a handle on it. Let me just give you the units before we move on. Do that in green. So force has a unit of newtons, named after Sir Isaac Newton. Mass, as you should probably know by now, is measured in kilograms. I know some things are given in grams and like tons and pounds and stone, depending on where you are in the world, but when we're doing physics calculations, we put it into kilograms because that is what's known as the standard or the SI unit. Now, acceleration has a really wonky unit because of how you work it out. If you don't use F equals ma, you might be expecting it to be something like newtons per kilogram because it's force divided by mass. But typically, when you're doing this topic, you also look at acceleration and velocity, and you meet that A is equal to the change in velocity over time. So change in velocity or change in speed, if you like, divided by time. So the typical unit, and I'm going to write this in power form, is this. ms minus 2, which is equivalent to saying meters per second squared, which is meters per second, the unit of speed, per second, because I'm dividing by time again. So I've got change in velocity, meters per second. Time taken, seconds. Meters per second gives the normal unit of acceleration. Sometimes you will see, particularly with gravity, the unit written as newtons per kilogram, as I've seen done. I did it myself in my gravitational fields video a while ago, but that's for A level. You don't need to see that for this. So that's Newton's second law. This will make more sense later, and we will probably come back to it and put it all together at the end. So Newton's third law is summed up very quickly, but it kind of belies a little bit of the information underneath. So we're going to go through it in full, just first, and then we'll explain what we mean, same as we have for the other two laws. So Newton's law says, roughly speaking, there is various variations you can look up online. If an object, which I'm going to call A, exerts a force on object B, then B exerts a force on A of equal magnitude, which is the sort of fancy word for size, and is generally used for vectors to say they have a magnitude instead of a size, equal magnitude and opposite direction. So equal magnitude and opposite direction. So that's the long-winded version. You've probably seen or heard it summed up a little bit faster by the following quote. Every action has an equal and opposite reaction. Much shorter, much simpler, but it doesn't tell the full story, which is why I've given you this longer quote. So, the best way that I can demonstrate this is for you to do this at home. So, go find anything. In fact, I'm going to sort of spoil the trick of the trade. I do these videos on my hob because it's the best lit area of my flat that I can stand at. If you push on that surface, it could be on the wall, it could be on the floor, it could be on the chair you're sat on the table in front of you, on your computer or your phone even, push on it and you will feel that the object pushes back against you. So, for example, if I push against the wall, I can lean on the wall. You can sort of see the shadow running along my arm. I can sort of lean there because the wall is exerting a force on me equal and opposite to the force I'm putting on it to hold me up. It is pushing back against me to keep me in place. And think about this, if you like, in terms of Newton's second law, and if this law didn't exist. So Newton's second law, if we remember, say if you apply a force to an object, there is an acceleration. Well, if you lean on the wall, for example, or you sit on your chair, you are applying a force to that chair. Or you could say that, for example, if it's your weight, which is a type of force, then the earth is applying a force to you. Yet you don't move. There must be something acting against you, an opposite force pushing you back up to hold you in place. And that is what Newton's third law is all about. It's really, really difficult to visualize in your head, but it's actually something that happens all the time. We see this, every action having an equal and opposite reaction all the time. It's what allows us to stand on the floor even, because bear in mind, you have a force. In fact, I'll show you this with a quick drawing. We're going to get onto force diagrams in a moment, but you as a person have a weight, and that weight acts towards the center of the earth. You might have seen that before in some of my previous videos. Well, at that point, if that's the only force acting on you, your weight, you're going to go downwards because of Newton's second law. Because it's the force, there's no force against it to balance it, which we'll get onto again in a moment, so you should fall right down to the center of the earth. But you don't, because the floor exerts an equal and opposite force, usually called the reaction force, on you. And those two forces cancel each other out to keep you stock still where you are on the surface of the earth. If Newton's third law did not exist, then we would just, well, we wouldn't be here. Let's put it that way. A lot of things we take for granted wouldn't happen if it wasn't for Newton's third law. So those are the three laws. I hope I've explained them as best I can. We're now going to talk about force diagrams and then calculate some resultant forces from that, and hopefully that will help to contextualize especially Newton's first and second law, which have been a bit wordy up to this point. Newton's third law is quite simple to conceptualize. The other two, I think we're going to need some diagrams, so let's do that. So up to this point, we have given you Newton's laws, but a lot of that kind of is a bit wordy. So now I'm going to try and show you what that actually means. And I'm aware this video is going on really, really long, so I'll do my best not to waffle anymore. We'll see how that goes. So Force diagrams, these are what you do very often. You sometimes see them called free body diagrams in exams, but they work pretty much the same way. So, when you're drawing forces and labeling and demonstrating that forces are there, you draw them using an arrow. For example, this. The size of that arrow and the direction it points in will depend on the force. So if you have a big force, you draw a big arrow. If that force is to the right, you draw an arrow to the right, and so on and so forth. So let's say this block is really, really heavy, and so its weight force is really large. And weight, as hopefully you might have picked up before, acts downwards towards the center of the earth. Now, you can draw your arrows like this, but I prefer them like this. I have a really big arrow, and I will label it with the magnitude of the force, say 500 newtons. So that thing weighs about 50 kg, for example. However, that diagram is not complete. You have to do that for each force. So remember Newton's third law, we have that reaction force as well from the ground holding the block in place. And that arrow has to be 500 newtons upwards. So however long this arrow is, this arrow must be the same size. You have to get your arrows to match up in terms of scale. So if you do it on like squared paper, it's very, very easy. But if you've got a ruler, you can eyeball it and get your labels correct. So that's 500 newtons upwards from the ground in order to balance the forces. However, you don't have to have just those forces. You can have many more. So if I come to my terrible looking car here, I might have a downwards force from the weight, an upwards force from the ground, which are equal and opposite. I'll then have my forward force from the engine, a thrust force, and I might have a small backwards force from friction, which is between the road and the wheels, slowing me down a little bit. You can have several arrows at once, and you have to do it for each and every force when you're doing your free body diagram. Once you've drawn your diagram, you can then move on to calculate resultant force, and that's where Newton's laws start falling into place. So, resultant force, this is what we actually use force diagrams for. So once we've drawn our arrows on our force diagram or our free body diagram, we add up all the opposite pairs of arrows, and I do mean opposite. So if I have a diagram where I've got an arrow to the left and an arrow to the right and an arrow downwards, I would add up left and right and up and down. Now there's no arrow here for up, so I treat that as equals 0. But I subtract each of the opposite pairs from each other. So if this one was 5 and this one was 3, then the resultant would be equal to 2 to the left, because it's 5 left, take away 3 right, and you do that for each opposite pair. If, and this is where Newton's laws come in, if all the pairs add up to 0, so those two, take them away, equals 0, those two, take them away, equals 0, if they all add up to 0, then we say that the forces are balanced. That means that Newton's first law is in effect, which means, remember, that the object does not change its state of motion because there is no overall force acting on it. The forces cancel out, and so the object carries on, staying still or moving at a constant speed. However, if there is any single unbalanced force, so if any of these pairs are not equal, then we end up with a force of not 0 in any direction. We say that the forces are unbalanced. Again, unbalanced, and that means that Newton's second law kicks into play. And that means, therefore, we have a leftover force, the overall force to act on the object and cause it to move and or accelerate, at which point we plug it into F equals ma in order to calculate that acceleration. Now, I'm going to show you one worked example of this, and then I'm going to get you to do some questions, because I realize this video has gone on long enough And I want to come back to the thought experiment that we had at the start of the lesson to bring this all together before we wrap it up. So for our worked example question, we have a block with a mass of 3 kilograms, which is being pushed to the right by a force of 100 newtons, and there is a frictional force that has a magnitude of 20. First part of the question, calculate the resultant force. Here we go. First, I need to draw my diagram. So, block, it's being pushed, and it's being pushed to the right. Now, because you've got friction, I've sort of been able to interpret, you'd probably be given the diagram in a question. So that's your diagram. So now we need to label our forces. First off, big arrow to the right, 100 newtons. Smaller arrow to the left, because friction always goes in the opposite direction to motion. I'm not getting into the details of friction here. I'm going to have to make the assumption that you know where I'm going with that. Look into friction if you need to. So there's 20 newtons now acting to the left. However, this is not a complete diagram. The object has mass, so it has a weight. And I know, I could work out it's about 30, but I'm not going to draw it. I'm just going to label it W and have my reaction force equal and opposite, because it doesn't actually matter for those two. Because those two are equal and opposite, they're going to cancel out, that's all good. So my resultant force is 100 to the right, take away 20 to the left, and that leads to 80, I'll put those in brackets, is 80 newtons to the right. That is the resultant force, and sometimes they might ask you to draw that on. So the resultant force is a little bit shorter. It is 80 newtons. That is your resultant force. Now, part B of the question, which I didn't write down because I wasn't sure how much space I was going to have, asks you to work out the acceleration. So let's just clear that very, very quickly. So I'm going to write F equals 80 newtons up there. So part B says calculate the acceleration. All you need there is Newton 2. So Newton's second law applies. So we know the formula from earlier, F equals ma. We know F equals 80 newtons, m equals 3 kilograms. All the units are good. So we just need to rearrange this equation a bit. If you're a formula triangle person, then you can have this, that F equals ma. So acceleration is force over mass. F divided by m equals 80 divided by 3, which I can do in my head, but I'm going to put in my calculator here. 80 divided by 3 is 26.7, if we round it off, 26.7 meters per second squared. That's broadly how a resultant force question and then a force equals mass times acceleration question will go. You'll get a lot of practice at this, I expect, when you do it at GCSE yourself at school. I'm now going to put up on screen a series of 3 questions for you to do. Reminder, I'm not going through the solutions in this video. I have shown you a worked example. I'm not going through them here. Click the link in the description for the solutions to those questions if you attempt them. Please do, because I'd like you to, and we'll go through them there. But for now, have a go at the questions, and when you're done, we're going to come back to that thought experiment we had right at the start, discuss what we learned today in that context in order to wrap up the lesson. So to close out today's lesson, I would like to return to our individual sat in their armchair. The very first thing we discussed right at the start of the lesson, that thought experiment that we've had in the back of our minds, hopefully, as we've gone along. So you might remember I asked you 3 questions. The first question I asked is, why is this person not moving? And the second question I asked is, what would make them move? And the third question I asked referred to the carpet. Why don't they fall through the carpet? So let's go through that, because I think hopefully you should know the answers by now. And unlike the solutions to the calculations, I think this is something worth keeping in. So we're going to use this to close out. So first question, why aren't they moving? So a few naive or perhaps unclear answers would be to suggest no forces. So you might say, oh, there's no forces acting on them. And that would link into Newton's first law. So remember, Newton's first law says an object can only change its state of motion if a force acts on it. Well, they're not changing their state of motion, so there must be no forces in play. But unfortunately, that's not quite right. You see, forces are around us all the time. In fact, in this system alone, there's 4. At least 4 in play. So let's take that into a force diagram, shall we? I'll make this a much simpler drawing than that one, and I'll draw it over here. There we go. So that's now my force diagram, which is slightly more complex, but it will do. So think about the forces that are acting in that system at this time. So I told you there are 4. The first one, perhaps the most obvious one, is to think about the fact that our person has mass, and as a result, that person must have a weight. All objects pretty much have mass, so they must have weight, which is a force that we haven't really discussed at length today, but is equal to mass multiplied by gravitational field strength. So that means that the person has a weight, which I'm going to call lowercase w. I'm only calling it lowercase because you'll see why in a moment. So I'm calling it lowercase w. And that is the weight of the person. So therefore, this answer of there being no forces must be wrong. But why therefore aren't they moving? Well, that comes back to our idea of resultant forces. You see, there is an upward force, which I'm going to call R, which is a reaction force from the chair on the person. So the chair is, if you like, holding them up, because when you sit on a chair, you don't fall through the chair. There must be a force opposing your weight to push up so that you don't fall through the chair. And that force I'm going to call the reaction force, and that is Newton's third law. Every action has an equal and opposite reaction, and so on and so forth. You put a force on the chair puts a force on you, and that's the reaction force that holds you up. There are actually 2 more forces, but I'll save those for later. But if therefore the object or this person is not moving, what can we say about their forces? Well, we must be able to say, coming back to our resultant forces, that the forces are balanced. Or you could say the resultant force is 0. So you could say that the resultant force is 0 because that means the same thing as having balanced forces. The weight force is equal to the reaction force of the chair on the person, and so they cancel each other out. The resultant force is 0, and the forces are therefore balanced. Now, the second question, what would make them move? Well, the answer is actually very, very simple. You apply a force, and that essentially is Newton's first law. So this is coming from Newton's first law from one angle and saying that balanced forces means no change in the state of motion, so they just stay still. But if you apply a force, then you get a change in the state of motion, and that then leads to an acceleration, which means that they change speed and therefore start to move according to Newton's second law. So if you apply a force and cause an acceleration, that is what you do in order to make them move. You apply a force, for example, you push the chair or you tip the chair, whatever it is, and you make them accelerate because the forces are no longer balanced. So we unbalance the forces. These are all just sort of notes that you can be making. And the third one is about the carpet. Why don't they fall through the carpet? Well, the answer to question 1 tells us this. There obviously must be balanced forces. But what are those forces? Let's return to our diagram. So now what I'm going to do is I'm going to say that the person and the chair are pushing down on the carpet. So I'm going to put that force there. I'm going to make it slightly bigger. And I'm going to call that capital W, the weight of the system, which is the person's weight plus the chair's weight. And that is the overall downward force on the floor. However, by Newton's third law, there must be a reaction force. In fact, this force should be coming really from the floor. A equal and opposite, which I'm going to call N, the normal force. This normal force, N, is equal to WS, the weight of the system, and it cancels it out, if you will, and that is because of Newton's third law again. So we say that there is a force from the carpet on the chair / person, and we'll make reference to Newton's third law to say that those forces are equal and opposite, and by Newton 1, balanced forces. Therefore, no acceleration. So that's the thought experiment in total. The person isn't moving because all of their forces are balanced. There's possibly some sideways forces as they lean on the chair, and there'll be a reaction force horizontally, but we're going to ignore that. Basically, the resultant force on them, their resultant force as a person, is 0. If you want them to move, you need to apply a force. By Newton's first and Newton's second law, you unbalance the forces and cause an acceleration. And then why don't they fall through the carpet? Well, it's the same as this up here. There's a reaction force, and the normal force, as I've called it here, from the carpet, which is on the person and the chair, on the whole system, which is again Newton's third law. And by Newton's first law, if the forces are balanced because they're equal and opposite, then there must be no acceleration, so they cannot start moving by falling through the carpet. Now, if there were no carpet there and they were just falling through space at a constant speed, that would also apply, but that gets a little bit more complicated, so I'm not going to get into that here. And that's it. That is all for today's lesson. That is our look at Newton's laws and resultant forces. If you haven't checked the solutions videos for the calculations and everything else, and you have done them, then the links, I'll remind you, are in the description below. Go and have a look at them. Make sure you're happy with your answers and how I've gone about doing them. Let me know your thoughts in the comments down below, and if you have any suggestions for future lessons, please do let me know. I'm looking to do stuff to do with momentum and impulse, probably mostly at GCSE level, but it is very similar to the A-level material, just slightly easier numbers most of the time. So quite simply, it's sort of a crossover between GCSE and A-level physics, so it can kind of serve for both. So look forward to that in the near future. and let me know what you would like me to cover going forward. But in the meantime, thank you very much for watching. This has been Tactica Imperialis, and this has been the Tactica Tutorialis lesson for Newton's laws and resultant forces. Thank you very much for watching, and I'll see you all again. Goodbye.